Proxima Centauri b, a planet orbiting the nearest star to our Sun, has become a focal point in the astronomical community. What sets this planet apart is how remarkably similar it appears to Earth in certain aspects, despite being over 4 light-years away. Its location within our cosmic neighborhood raises exciting possibilities regarding extraterrestrial life and even future human settlement. The global scientific community has long been intrigued by planets that may not just support life, but potentially offer conditions more favorable than those on Earth. This groundbreaking notion, popularized by influential minds such as theoretical physicist Michio Kaku, has shifted the trajectory of space science. Instead of limiting the quest to Earth-like planets, researchers are now considering the existence of superhabitable worlds, planets that might actually outshine Earth in their ability to support life. These exceptional planets may possess climates that are more temperate, broader regions of arable land, and more stable ecological conditions. Imagine a planet with a mild global climate, a wealth of freshwater lakes and rivers, and expansive forests that stretch for miles, all under skies gentler than Earth's stormy atmosphere. These could serve as better cradles for life, perhaps even surpassing Earth in biological diversity and environmental harmony. For years, the holy grail of planetary research was to find an Earth 2.0, a twin world, similar in atmosphere, surface conditions, and size. However, breakthroughs in observational tools and data interpretation have expanded our view. Today, the possibility of encountering worlds that go beyond Earth's potential is no longer speculative. It's becoming an accepted scientific pursuit. Michio Kaku has long advocated the necessity for humans to become an interplanetary species. He argues this is not merely an ambitious dream, but a safeguard against catastrophic threats. Earth remains susceptible to planetary-scale dangers like asteroid strikes, supervolcanoes, or long-term climate shifts driven by solar evolution. In about 5 billion years, our Sun is expected to swell and engulf the inner planets, including Earth. Seeking alternative worlds isn't just exciting. It's a necessary step for the survival of our species. Rather than limiting exploration to planets that mimic Earth, researchers propose aiming higher. Worlds that exceed Earth's life-sustaining characteristics, so-called superhabitable planets, may provide clues about ideal environments for nurturing complex life. Back in 2014, scientists Renee Heller and John Armstrong proposed a revolutionary view on planetary habitability. They argued that being located within a star's habitable zone, where temperatures might allow for liquid water, isn't the only factor to consider. A planet's internal energy, geological activity, age, and other physical characteristics play vital roles in determining its ability to sustain life. Liquid water is a cornerstone of life as we understand it, guiding much of our search for habitable worlds. But Heller and Armstrong suggested that other configurations might be just as, if not more, capable of supporting life. Planets with more stable climates, diverse ecological niches, and consistent energy sources could present better prospects for long-term biological development. Some of these worlds might sustain ecosystems far more complex than those on Earth. Consider Europa, one of Jupiter's moons. Beneath its icy crust may lie a subsurface ocean that could harbor life, despite being nothing like Earth's surface. This suggests that limiting ourselves to Earth-like environments may blind us to life in other forms or habitats. That's why the Earth analog approach may be too narrow. It may be more fruitful to seek planets that offer the best combination of features for life, regardless of how much they resemble our home. Moving away from an Earth-centric model enables scientists to expand their understanding of where and how life might arise elsewhere in the universe. Heller and Armstrong's theory sparked a new direction in exoplanet studies. They outlined the essential traits that might make a world better than Earth, incorporating features such as moderate size, optimal mass, sustained tectonic activity, and the ability to retain a thick atmosphere. They also broadened the scope of target stars beyond those resembling our Sun, advocating for attention to more stable stars like orange and red dwarfs. Among these, orange dwarfs offer compelling benefits. These stars, though dimmer than the Sun, are remarkably stable and can live for tens of billions of years, many times longer than our Sun. This immense time span increases the likelihood that complex organisms could emerge and thrive. Since Earth's most advanced life took billions of years to evolve, planets orbiting such long-lived stars may have had a significant head start. Still, there's a balancing act. If a planet is too old, it might lose internal heat needed to maintain tectonic shifts and magnetic fields, key features for sustaining life. These planetary systems help recycle essential elements and shield life from harmful radiation. Heller and Armstrong suggested the sweet spot for planetary age lies between 5 and 8 billion years, just enough time for life to mature without compromising geological vitality. Earth, by comparison, is relatively young at about 4.55 billion years. A planet's mass and radius are equally crucial. While the habitable zone remains a basic guideline for the presence of liquid water, planetary size affects everything from biodiversity to atmospheric stability. A planet just 10% larger in radius than Earth could boast greater environmental variety, larger forests, more expansive oceans, deeper valleys, and more geographic diversity overall. This diversity could foster more life forms and more complex ecosystems. On a larger world, the combination of diverse climates and ecosystems could drive evolutionary adaptation at a faster or broader scale. From dense rainforests to expansive wetlands and dynamic coastlines, a larger surface area could offer the space needed for a richer biosphere. Furthermore, increased mass improves a planet's ability to retain a thick atmosphere. Stronger gravity helps hold on to crucial gases that moderate climate, distribute heat, and shield the surface from solar radiation. Without such an atmosphere, a planet's surface would likely be too harsh for life. Earth's atmosphere regulates temperature and protects organisms from harmful rays. On a superhabitable world, this envelope might be even more efficient. A denser atmosphere also supports a more dynamic water cycle. It facilitates the formation of clouds, rainfall, and surface water, all vital for supporting plant and animal life. These features play a key role in nutrient cycling and contribute to ecological equilibrium. Another important factor tied to mass is long-lasting internal heat. Heavier planets tend to hold onto radioactive elements for longer periods, fueling the geological engine that powers tectonics and volcanic activity. These processes not only help maintain a magnetic field, but also replenish the surface with essential minerals. Without tectonic activity, a planet's habitability declines over time, just as it did on Mars, which lost its magnetic shield and much of its atmosphere. Of course, higher gravity comes with trade-offs. Life forms, including future human visitors, may struggle with mobility in stronger gravitational fields. However, many scientists believe the habitability benefits vastly outweigh these challenges. Such planets may also feature warmer climates and more expansive land areas, promoting lush vegetation and rainforest-like ecosystems. On Earth, such environments support the greatest biodiversity. A planet with slightly warmer average temperatures, abundant rainfall, and a balanced distribution of land and water might offer an even more vibrant biosphere. The arrangement of land and sea is another significant factor. A balanced geography, where lakes, rivers, shallow oceans, and various landforms exist, creates diverse biomes. On Earth, coastal areas often teem with life, serving as some of the most biologically productive zones. A similar distribution on a superhabitable planet could lead to even richer ecosystems. Out of the over 5,000 confirmed exoplanets, scientists have pinpointed at least 24 that may be more suitable for life than Earth. Among these, KOI 5715.01 stands out. Located roughly 700 light-years away, this world orbits a stable yellow dwarf star. It is believed to be around 6.5 billion years old with a surface temperature of approximately 80 degrees Fahrenheit 27 degrees Celsius, and a size ranging between 0.72 and 1.29 Earth radii. These parameters make it an excellent candidate for habitability. Although many of these exoplanets lie far from Earth, they are becoming increasingly accessible for study. Next-generation telescopes like the James Webb Space Telescope, JWST, are equipped to examine their atmospheres in detail. Scientists hope to detect biosignatures, gases like oxygen, methane, or other organic compounds, that could indicate life. Proxima Centauri b continues to captivate astronomers and space enthusiasts alike due to its proximity and potential habitability. Located just 4.2 light-years from Earth, it orbits Proxima Centauri, the closest known star to our solar system. What makes this exoplanet especially compelling is that it lies within the habitable zone, often referred to as the Goldilocks zone, where temperatures might be just right for liquid water to exist on its surface, a fundamental ingredient for life as we know it. Being in this life-friendly zone gives Proxima Centauri b a distinct advantage in the ongoing search for potentially habitable exoplanets. Liquid water is essential for biochemical processes, and the possibility that this planet might support it has led scientists to prioritize it for detailed study. Its relatively short distance from Earth also makes it one of the most accessible targets for future exploration, both observationally with telescopes and hypothetically through interstellar probes. However, despite its promise, Proxima Centauri b is not without significant challenges. One of the most critical concerns is tidal locking. Due to the planet's close orbit around its parent red dwarf star, it's likely that one side of the planet always faces the star, while the other side remains in perpetual darkness. This condition could result in extreme temperature contrasts, blistering heat on the day side and freezing cold on the night side, posing serious difficulties for maintaining a stable, life-supporting environment. The narrow terminator zone, the region between day and night, might offer more moderate conditions, but it is uncertain whether this region would be large or stable enough to support life. Moreover, Proxima Centauri itself is a highly active red dwarf star known for its frequent and intense stellar flares. These powerful bursts of radiation, including ultraviolet and X-rays, can be extremely damaging. Over time, such radiation can erode a planet's atmosphere, especially if the planet lacks a strong magnetic field to shield it. This atmospheric loss would dramatically lower the chances of surface liquid water and biological life. Even if an atmosphere exists today, it might be thin or in a state of continuous renewal due to constant bombardment. Despite these challenges, Proxima Centauri b remains a primary candidate in the quest to find habitable worlds. Its proximity offers an exceptional opportunity to study the conditions of planets around red dwarfs and to better understand the complex balance between habitability and environmental hazards. Nonetheless, its closeness to Earth makes it a prime candidate for study. It represents a valuable opportunity to learn more about the limits of planetary habitability and test our models against real-world data. Future missions may reveal whether its challenges can be overcome or if better prospects lie elsewhere. Ultimately, mounting evidence suggests that Earth might not be the pinnacle of habitability. Slightly older, larger, more massive planets with optimal environmental conditions could offer a richer tapestry for life to flourish. As technology propels us further into the cosmos, we'll be better equipped to find and analyze these worlds. Our approach to space exploration is evolving. No longer confined to seeking Earth's twin, we are expanding our horizons to identify planets that are even more welcoming. By embracing the broader spectrum of potential habitability, we may uncover worlds that are not just suitable for life, but ideal for it. The true promise of our cosmic journey lies in the discovery of such extraordinary realms, where life may bloom in forms and richness we have yet to imagine.